Hello and welcome to this video where we talk about physics and mathematics on the board. Here there's going to be physics, and in fact that's actually connected to a video that has been published recently on whether or not magnetic forces do work. And it comes from a very kind of famous, infamously I would say, uh, notorious statement from Griffith in his textbook that states that magnetic forces do no work kind of whatsoever. Okay, um, and no matter the kind of systems we look at, magnets interacting with magnets, magnets interacting with metals, magnets interacting with wires, whatever, actually magnetic forces do no work. And the video actually was discussing quite a bit about how we explain nonetheless, like all the phenomenology where seemingly magnetic forces appear to be doing work. Um, and unless I missed something, it seemed to me that the conclusion from the video was kind of twofold. Is that salvation seems to be found in not in the like freely moving, so in the Lorentz force is kind of doomed, and so salvation is found in how magnetic fields interact with point dipoles, and therefore it's mostly found in kind of quantum mechanics with the electron spin, intrinsic spin, for example. But then, more interestingly, there is a sort of aha and um, kind of some happiness toward the end, where apparently you could have a model of an electron or a classical kind of spin for electrons, and so that's actually where the work could come from. And I think I would like to propose alternative ways of conceiving how magnetic fields actually give rise to forces that actually do work, and how, in fact, all of these different things need not be incompatible with each other via mechanisms that I'm going to explain. So that's what we are going to do today. I hope it's not going to be too long, but we'll see. Right, so again, in the video, the corresponding author essentially was only looking at magnets, and magnets are related to models, like the Ising model, for example, that is going to involve some spins, and then the spins are going to interact via some, so in some way that are either trivial, like some product of their values and so on in some neighborhood and so on. So that's kind of the idea, and that was the main focus of magnetism and of the discussion on magnetism and forces. Now, I would like to depart from this view because, of course, magnetism is also found in basically in the phenomenology of wires that carry current. And that's the example I drew here, whereby if you've got a particular portion, a straight portion of wire of a circuit, or that is traversed by a current that goes, let's say, up, then it's going to generate a magnetic field around it. Okay, and then if next to it you've got a straight portion of a circuit with then in that case the current going this way, then via the right hand rule, for example, you're going to get that there is a force that is exerted that way. So basically the wires are going to repel each other in this particular case. Now, if the current were going the other way, then you will actually get attraction. Now, the reason why this is actually very, very important indeed is because this particular experiment on the forces between two wires is actually what defined the ampere, okay, which is a unit of measuring intensity. And in fact, the ampere is the actual intensity of current that needs to go across these two wires separated by 1 meter, so that the force between the two is actually 1 Newton. Okay, so that's how you would define it. So it's a precise definition that is used in calibration and so on, and it relies on the magnetic forces between these wires. Um, and so I think we need to understand a bit what's going on there. And obviously, these forces do actually work. Okay, so they do work. Okay, so we need to understand what's going on. And the way I want to do it is to try to understand the mechanism by which a magnetic force is going to give rise to essentially a work that is being done by some other object. Okay, and and so here I'm trying to model, like very crudely, of course, a mass spectrometer. And what I have is an incoming, let's say, electron beam. So I'm not sure, will I get it right? We'll see. So I'm going to get an electron beam here. And so here, these are the electrons that are moving with this particular velocity. So what that means is that the current is going this way. So hold on, did I get this right? Probably I didn't. So this is going that way, then this is going that way. So then that would be this way. So okay, so that's not. So let's say here, for the sake of it, these are positrons. Okay, so we've got positrons that are actually going into a particular chamber and then into a mass spectrometer. You can imagine these are protons. It doesn't matter really what they are, as long as you get the trajectory right, which I didn't. So the thing is, you've got this charged particle coming in, and upon getting into the magnetic field, they are going to feel the Lorentz force. Okay, the Lorentz magnetic force, which is F, is equal to, so in any case here, that's going to plus E, and then the velocity cross B. Okay, so that's a cross product, and here the velocity is V here. Okay, so what's going to happen is that once it enters there, it's going to feel a force, and this force is going to deviate essentially the trajectory this way. So there is, as soon as it enters, it feels a force, like the Lorentz force, that is going to deflect it this way. And in fact, the way it's going to deflect it is always going to be perpendicular to the direction of motion. Okay, and that leads naturally to a circular motion. And so here, what you can assume is that, for example, you're going to get a curve like this for the deflected beam. Okay, and let's assume that at that point, I'm just going to put some dots here. The magnetic field is stopped, so it's uniform here, and then it's stopped there. So then what the positrons do is that they simply continue straight. So you've got basically some kind of trajectory like this. And what is fascinating in this particular mechanism is that the kinetic energy has been unchanged. Okay, and the way to see that is to see that if you have half mv squared, that's the kinetic energy, and then in that case you're going to get, if you look at the time derivative of that stuff, you're going to get that this is m and then v dot dv dt. dv dt, m times dv dt is the force, and so you're going to get that this is basically E v cross b, and then dot v, which is 0. Okay, and that's 0 because the cross product of v and b is always perpendicular to v, and then the dot product with v is going to give 0. So the bottom line is that there is no change in the kinetic energy when the trajectory is actually deflected. Okay, the particle's trajectory is being deflected. That being said, once the actual particle gets into like the detector, is going to be stopped. So there is a sort of there is a stopping energy or stopping work being done over a certain amount of space, which I don't know, okay? What I know is that the stopping work has to be equal to the initial kinetic energy. So stopping work that is being done, and that's equal to K itself, okay, to actually stop the incoming very fast kind of particle. Okay, so what I see here is that I've got a magnetic field, and what this magnetic field has done is basically transferring energy from the electrons that are kind of moving in some, some direction with some velocity, and then basically making them smash onto a detector. As they do so, and as basically the detector itself is actually exerting a force on the, I say electron, but that's a positron here, on the particle, then basically they do work on the particle to actually spend, if you will, that kinetic energy. Likewise, the particle is exerting actually a force which does work on the detector. And in fact, if we could observe, the detector surely would actually move. Okay, it moves like a tiny bit because it's a tiny object, but it moves a tiny bit kind of backwards, if you will. If you were to imagine that there is a spring or something, it would actually move that way. Okay, so there is an imparting of momentum from the particle that is actually going to heat there. And that's kind of what I think is actually going on. The magnetic force is actually deflecting uh, energy that comes, for example, in the form of kinetic energy, and then using it in that particular case to actually hit something. Now, the question is, how does that work in this particular situation? I'm just going to propose a model, and then of course you feel free to criticize this particular view if you want. The view and the model I'm proposing is going to be crude, and it should not be conflated necessarily with these things, because here these things actually move at close to the speed of light. So of course we are not talking about the same things, while the drift velocity in a wire, as I'm going to show here, is about like a centimeter per second, or something, or even smaller. So we are not talking at all about the same kind of velocities and speeds. Nonetheless, let's try to have a look at what would happen. So here, let's imagine that this is a zoom in onto the wire. Okay, and the only thing I'm going to draw here is yeah, for example, I'm going to draw this particular situation. Okay, so I have an electron flow. So here these are electrons that are flowing then that way. So these are electrons this time are flowing with a particular drift velocity that is, let's say, v. And that's basically what I have. Okay. Now the corresponding intensity is minus the charge, so that's going to be in that direction. So I'm kind of in line with what is there. Okay. And basically that's it. Now, when I'm going to put this into a magnetic field here, so there is this magnetic field that is going to be there, and let's say here. Okay, so we've got a magnetic field here. It's going to actually deflect the particles are going to be deflected. Okay, so there is going to be a deflection here, force. And this deflection is related to the drift velocity and the charge of the electron and so on. Now, this is going to do the following. So there is correspondingly a sort of trajectory that goes like this. And then, okay, I'm exaggerating a lot here, and that is going to go towards, essentially towards the wall here. So there are kind of walls onto the wire, okay? Now, what's going to happen is that the is that there is, for this velocity, when it arrives here, there are two components. There is a component that is that way, that I'm going to call V parallel, so parallel to the wire. And then there is a component here, which is V perpendicular to the wire. Okay? And in the same way here that we actually had the stopping work that is done by the detector, here we need to have a work that is done by the metal or by the wire, depending on the kind of material it's made of, that is made by the wire to prevent the electron from actually leaving the medium. So there is, I mean, of course, you can translate that into some harmonic force, depending on your model. You can put that in a Morse potential. Whatever you do, there is a sort of force, and you have not yet, reached any kind of critical value to exceed the actual thing. So at the bottom of it, you're going to get that the wire. Okay, so first exerts. So that's the first step. Exerts a force. A force onto the electron. Okay, to stop it. But it doesn't stop it at all. It stops it only. It doesn't need to stop it for all directions. It only needs to prevent it from, and it only. It's not even need because that's a bit too anthropocentric terminology. It just does stop it in this particular direction, because there is an actual kind of symmetry breaking here that does not appear in the vertical direction. So to stop it, and it then basically does work that corresponds to K perpendicular, which is half of M and then V perpendicular squared. Okay, so there is some work that is actually done there. But on top of it, it's not enough, because at all times, even if the V parallel remains, you still have a force that is going to be always like that. And so the second aspect is that the wire is going to, so this force eventually balances the Lorentz force. And the Lorentz force is going to be minus E, and then V, that's V parallel, and then cross B. Okay? So that's kind of the idea here. What is remaining here in principle should be the V parallel, and my view on this is that the V parallel is actually related to the magnetoresistance of the wire. Okay, so that's the thing, is that it exerts a force that balances the Lorentz force, and because it balances it, is going to be plus. Okay, so the force from the wall, from kind of the wall of the wire onto the electron, is going to be plus E V parallel cross B. Okay, but then once we're there, we're like, okay, fair enough. That's the force exerted from the wall onto the electron, so that basically the electron cannot leave. That's a response, if you will, from the wall. But then we finish the story by saying, well, Newton's third law tells us that the electron is going to exert the opposite force to that of the wall on the wall. So Newton's third law is going to tell us basically that the force from the electron onto the wire, if you will, is going to be equal to minus the force balancing it, and it turns out is going to be exactly that. So that's going to be minus E, and then V parallel, and then cross B. Okay? Now, usually what people do at that stage is that they neglect the magnetoresistance effect, and then they claim that V parallel basically can be connected kind of in very good approximation to the velocity in the drift velocity in the kind of normal current condition. And so if you say that V parallel is approximately equal to the initial V, then you get the final formula that the force, when you then try to add up all possible electrons in the volume that you've got to, that the force on the wire is going to be equal to I and then dl cross B. Okay, where I is the actual current. So that's when, once you have basically looked at the entirety of the charges in a given kind of volume here, you basically would get this IDL cross B, okay, for a particular element DL of force there. So in fact, that people would say that's a sort of DF or something like this. Okay, so the thing here, what is fascinating, at least with this particular interpretation, is that the force and the work, there is genuine work that is going to be done, because overall there is a resulting force onto, if you've got a portion of wire here that is, let's say, DL, you're going to get a corresponding force on the wire, which is in that direction. And that results from the momentum that is imparted onto the wire by the electrons that are subject to a drift velocity and the non-working magnetic force. Okay, and essentially the physics that at least I wish to propose here is very similar to this one. The mechanism is very similar to this one, and basically give rise to, I need to put a D here just to make sure things are right, is very similar to that one. So that's what happens. The advantage of looking at it in terms of a wire and stuff like that is that I don't need to specify too many details for things to work out. And the cause or the origin of the force on the wire on the electrons is going obviously to depend on the kind of material and also the kind of model you have of these materials. But the bottom line is that it's not important as long as you say that essentially the electrons can't leave the metal or the wire in general. So to summarize, what happens is that magnetic forces, when they exert themselves onto freely moving electrons, are going to do no work. Like apparently, and that's convincingly at all times, according to Griffith and according simply to this like very quick calculation. They can't change the kinetic energy, therefore they don't actually do any work. However, by deflecting trajectories of charges, when these charges are not freely moving and basically are going to be in various bound potentials or interacting with other stuff, these electrons themselves are going to impart momentum and stuff like that onto the objects they interact with. And that's how the magnetic field manages to kind of convey forces that are roughly of the same magnitude as that is expected when you've got conducting loop of currents and stuff like that. Now, I'm going to finish by trying to answer a question, which is where does the energy come from? And here what we see is that in both cases, the energy comes from the pre-existing kinetic energy of the electrons. Okay, so you've got a pre-existing kinetic energy, which is basically fueled by an EMF, for example, and this particular kinetic energy here is going to impart some kind of momentum on the detector, for example, and here is basically going to push around things. Now, of course, the thing here is that we need to assume that the force here is really the force of the electrons onto the wire. Now, of course, if you try to do things in all like its details, then things become, of course, a bit complicated because you're going to get that the that if you take as a whole the electrons plus um, the um, the electrons plus the things they are subject to. Well, I mean, they are still subject to something. Okay, so um, no, I think it's fine. I think it's fine. So the bottom line here is to see the wire as being separate from the electrons drifting within it, and then see what are the interactions of the electrons with this wire as a separate object. And we see that then the wire is going to move. Now, consequently, the rest is going to move as well. It's a little bit like if you were to, if you have to push a box, but when you are completely within the box, then you can't, right? Because there is no external forces for you to push on or whatever. However, if you have a cardboard box which is just on top of you, and the floor below is accessible, you can push a box. That's what the electrons do. Okay, the magnetic field serves to some extent as this floor they can push on in order to exert force on the box. So that's it. So, like to finalize things, essentially the magnetic field is a sort of Tai Chi master, at least as far as I want to look at it. It kind of deflects the energy from from the electrons, for example, or from charged particles, and then basically mediate that energy to actually do work on other objects. And so whether or not magnetic forces do work, well, I think that it's fair to say that magnetic forces definitely mediate work, so that's for sure. And then in the case of whether they do work or not, then it depends on the kind of approximations we are making and the kind of phenomenology we want to keep as well. So I think there could be room as well to say that they do work, but then in that case, like the models and the specification of what do we mean by magnetic field, what do we mean by magnetic force in particular, would need to be more specified. Okay, so I'm pretty sure not everyone is going to be on board with this particular explanation. Personally, I think this worked quite well. However, if you've got any comments or things to criticize, by all means do so, and we'll see each other otherwise in another video.